Hi everyone, welcome to this video entitled Current Mode Push-Pull DC-DC Converter using the UC1846 Overcurrent Protection. So in previous videos we saw how to implement a push-pull converter using the UC1846. In this other video we implemented the closed loop design of the converter, and in this video we studied how to implement other housekeeping circuitry that is necessary for the operation of the push-pull converter in current mode. So today we are going to finish with this converter. We are going to see how to implement the overcurrent protection, the short circuit protection, and finally how to implement a hiccup short circuit protection. Here we have other interesting videos related to current mode control, so if you are interested you can take a look at these videos too. In this previous video, Qspice number 6, we saw the pins that are related to the current protection of the circuit. So we have pin number 1, which is going to act at the output of the error amplifier to limit the voltage and therefore limiting the peak current through the switches. And then we have the shutdown, which is another pin that we can use to activate this SCR here, and in this way turn off the operation of the switches. So here we have the numbers that we are using. In this case we have here a series resistance to measure the current through the switches is 0.5 ohms. We have used these two values for these two resistors here. So at this point we have something like 408 volts. As we have seen, we have this transistor here and this diode. So the voltage that we are going to have here at this point is going to be approximately the same as this voltage here, because these two voltages are going to be compensated. So the voltage at this point is going to be limited at this value here, 3.58 volts in our case. So the clamping voltage of VCS here is equal to this value divided by 3, as we can see here. So we have this value, and therefore this value divided by RS will give us the maximum peak value of the current through the switches. So the maximum peak current at the end can be obtained with this expression, and this is 2.39 amperes in our case. So let's see the simulation now, starting with the same circuit that we have from the last video. What we have done is to add here at the output a switch. So we are going to connect in parallel with the load a small resistance of 1 ohm, and then we will have an overcurrent. And here on this side we have at this point the pin number 1, and we have this resistance is 1K, this other is 4K. So at this point we have the value that we have seen, 4.08 volts, and this corresponds to a maximum peak current of 2.39 amperes. So let's run the simulation and see what happens. So here we have the simulation running. This is the current through the inductor. Here we have the voltage at pin 1 and the step voltage that controls the switch here at the output. This is the output of the compensator. This is the peak current through the switches, measured here at this point and divided by 0.5 to get at the end a value which is equivalent to the current through the switches. And below we have the output voltage. So we can see that at this point, when the output switch here is connected, we have an overcurrent through the inductor, but the current is going to be limited. So we can see this better here at this waveform. The maximum current, if we do a zoom, is going to be something like, if we look here at this point, we can see that is something like the expected value. Let's do another zoom. This point here is something like 2.37, 38. It's very similar to the value that we have calculated. So we can see that once we connected the small load at the output, we have a transient. The output voltage cannot be regulated, of course. We have a lower value, something like 3.8 volts at the output, because the operation of the converter is being limited. And then at this point here, we are opening the output switch. So then the current goes into the normal situation. We have this peak here, and then we recover the normal operation of the converter. And here at this point, we can see that the current is being limited to a maximum value of 4.6 amperes approximately at the output, while the actual value in normal operation is around 1 ampere. Also, we can see here how the maximum output voltage of the compensator is being limited to approximately 4.6 volts, which at the end limits the peak current through the switches, as we have seen in previous slide. Now let's see what happens when we do a short circuit at the output. So in this case we are going to connect here in parallel a very small resistor of only 10 milliohms, and we are going to close the switch at 1 milliseconds. So let's run the simulation and see the results. Now here again we have the simulation running, so we are getting 5 volts at the output, and at this point here we are closing the switch at the output. Then we have here in blue the sensing current, the signal corresponding to the current through the switches, and this is here the current through the inductor. So we can see how the current through the inductor is continuously increasing without limit. So our protection is not working well under this situation. And why is this? If we take a look around here, we can see that here we have normal operation, and in this part we have some very short pulses on the signals corresponding to the gates of the switches. So this means that our converter is still operating with a very small duty cycle, and this is the reason why the output current keeps increasing and increasing continuously. If we do a zoom here, we can see that there is a minimum duty cycle, a minimum on time for the switches. And this is so because if we look at the structure of the integrated circuit, we have here that we are continuously activating the switches due to the operation of the circuit. We have this oscillator, and continuously one of the switches is going to be activated, the other deactivated with each pulse of the oscillator. So at least the switches are going to be activated by a very short period of time. They are going to be off when the current that is circulating through the switch is above the limit of the comparator here, but then we have the response of the comparator, the response of all the circuitry. So this is the reason why we have a minimum on time for the switches even in this situation. So this type of protection using pin 1 under very high overcurrent at the output is not useful to do the protection, and then we will need to use the shutdown pin to protect under short circuit situation. As we saw in this previous video, the operation of the shutdown circuitry is as follows. When we inject here a pulse with an amplitude higher than 350 millivolts, the SCR is going to be activated. So the soft start capacitor is going to be discharged through the SCR. And then we have two possibilities. If we design these two resistors so that the current Vref divided by R1 is lower than 0.8 milliamperes, this current is not enough to keep the thyristor conducting. So it's going to be off again, and then we will have another cycle of soft start and the circuit will try again to operate. However, if we design with this condition, Vref divided by R1 higher than 3 milliamperes, then the current that is circulating through the thyristor is high enough, so the thyristor is going to keep conducting, and then the converter will be kept off until the power is recycled. So let's try this in a simulation. Here we have the circuit again. We are going to use this pulse voltage source to inject the pulse to the shutdown pin. Here is the shutdown pin. And then we have implemented here both situations. With this first one, we are using a small resistor here in this position, so this is 1K, so the current is going to be around 5 milliamperes. So in this situation we are going to be latched to off state. The thyristor is going to be kept conducting, and therefore the circuit is going to stop the operation. So let's run the simulation, and here we can see the operation. Now the output voltage has reached the 5 volts. At this point here we are injecting the pulse at the shutdown pin, and then we can see how the operation stops and it doesn't recover. We can maybe do a zoom here and see the pulses and how the converter is turned off. Now if we go here and comment this and uncomment this part here, now we are using a higher resistor RA here for this resistance, so the current is like 0.5 milliamperes, which is smaller than 0.8 milliamperes as we have seen in previous slides. So in this case we are going to have the recovery of the system after a period of time. So let's run the simulation again. Now it's running. Here we are with the voltage, output voltage at 5 volts. Now we have the pulse. We have a period in which we are disconnecting the operation, so we have no pulses. But after that we have another cycle of soft start. We can see that the voltage at pin 1 is again increasing, and then we are getting normal operation again. So the system is recovering after the pulse and it performs another soft start cycle. Now, as we have seen also in this previous video, we are going to try to implement an improved overcurrent protection using this circuit here. We add an additional resistor here in series with the sense resistor, and this voltage here is connected to the shutdown pin. So when the voltage here across this resistor is higher than 350 millivolts, the shutdown is going to be activated. We are going to avoid the latching of the thyristor here. So we will be designing with this value of the current Vref over R1 here. This is R1 as we know. And then we will have a soft restart of the circuit after a given period of time. This is called as Hiccup protection mode. So let's try this in our simulation. Here is our circuit. We are adding this resistor in series is 0.1 ohms. So in total we kept 0.5 ohms as in previous simulations, but we are adding this resistor. We are adding this filter to remove the spikes. So the signal at this point is going to be higher than 350 millivolts when the peak current is 3.5 amperes, and this will activate the shutdown circuit here. And here we are using a resistor of 10K, so we have not activated the latched mode. We are operating without latching. The current is going to be lower than 0.8 milliamperes, the current that is circulating through this resistance when the shutdown is activated. So let's see what happens now. So here we have the waveforms. We are now here at 5 volts as usual, and at this point we are doing the short circuit, so we can see how the current is increasing. Also the sensing current at this point is increasing, and when the sensing current reaches approximately, as we have seen, 3.5 amperes, so here at this point at the shutdown pin is something like 350 millivolts, then the shutdown is activated and the circuit is disconnected. But we were expecting here that after a period of time the circuit will start another soft start cycle. But this is not so in this case, and I have investigated this, and the problem is that when we generate the shutdown with a very short pulse as shown here, this is the signal that we are using to activate the shutdown, the thyristor continues conducting, and we can test this in our previous simulation in which we are driving directly the shutdown with a voltage source. If this pulse is something like shorter than 1 microsecond, the soft start doesn't start again. I am not sure if this behavior corresponds to the actual behavior of the integrated circuit, but at least using this model of the UC1846 we have this behavior. But I wanted to show you the hiccup protection mode. So what we are going to do is to implement externally our hiccup overcurrent protection. So let's see how to do this. So this is the circuit here that we have created to implement the hiccup protection mode. We are using an external comparator to compare the voltage here with the 350 millivolts. So at this point we are going to have a short pulse as we have seen. And from this short pulse we are going to generate a pulse here for the shutdown that is long enough. So this is going to be turning off the converter during a given period of time. So for this, what we do is to use this D flip-flop. So with this positive edge, we activate the output of the flip-flop. So it's going to be at level 1. And then we use this derivative network followed by this buffer to generate this pulse. So the duration of this pulse here is proportional to the resistance R19 and capacitance C7. So after this period of time, the shutdown signal here is going to go down automatically, and this negative edge is used in this circuit to clear the flip-flop again, so the Q signal is going to be down again. So from this negative edge we generate a short pulse. Again with this derivative network we can create a small pulse here, and this short pulse is going to clear the flip-flop. So here we have the circuit exactly as we have seen in previous slide. So now we can run the simulation and see what happens. So we have now the simulation running. We have reached the 5 volts here, and then at this point we have the short circuit at the output, and now we can see the hiccup operation mode. So when the current here, the sensing current, reaches 3.5 amperes, we can see how the shutdown is activated during a given period of time. After this period of time, it is deactivated again, and then the current is trying to increase again, but when it reaches again 3.5 amperes, then the shutdown is activated again, and then we have like a hiccup at the operation of the converter. So the trick here to have this hiccup mode is that the length of this pulse here for the shutdown is high enough, so during this interval the current is going to decrease, the current through the output is going to decrease. So when the pulse at the shutdown finishes, the current is going to increase again, but from a smaller value. So we are going to have another period in which the current is increasing, and then the shutdown is activated again, and so on. And here at the end we can see that if the short circuit disappears at the output, then when the shutdown, the last pulse at the shutdown finishes, then we will have a soft start again, and the converter recovers the normal operation with 5 volts at the output. We have this transient here at the output voltage because when we remove the short circuit, all the current through the inductor goes into the output capacitor. So it is going to be charged with all this current until the shutdown finishes, and then the soft start cycle starts again. So this is very interesting way to implement a short circuit protection in a DC-DC converter. Well, with this we finish today this presentation. I hope that you find this information useful. Please let me know if you have any comment or question, and I hope to see you in the next video. Goodbye now.